Yay, it's a set of telescoping gauges, the latest in hole measuring technology. So I picked these up for what I think is a fairly good price, $30. They are a little crunchy in places, so I'm going to have a try at cleaning them up a little bit. Particularly the screws are full of 50 years worth of crud probably. They're a mixture of Starrett and Brown & Sharpe. I think we'll have a little bit closer in a second. If you compare how much a set of these cost brand new, I think $30 is a bargain. Anyway, let's have a closer look. I'll switch over to a better lens. Okay, so here's the largest one. And I think that says B&S Manufacturing Co. I assume that's Brown & Sharpe, but I don't know that for sure. The next size down, where's our focus? The L.S. Starrett Co. There you go, Starrett. This one is a little bit rough. Then what's this? Another Starrett by the looks. This one is very sticky. And the smallest, another Starrett. Also pretty crunchy. 3 Starretts and 1 B&S Manufacturing. There is a bit of a gap in the collection, so I guess I won't be making any holes this size. Let's pull these apart, see if we can't clean them a little bit and get them to operate a bit more smoothly. Yeah, well, I'm not clever enough to get the Starrett gauges apart. The Brown & Sharpe gauge came apart pretty easy because it has a screw in the top. These Starrett ones, there's no obvious way to get into the head. But definitely the insides of the B&S gauge were pretty grimy and gritty. So presumably all of these are similar. Given that I can't get into them, I think I'm just going to soak them all in mineral turpentine and see how they are after a few hours. So here they are, nice and clean. I mean, they're still pretty crunchy, which is a little disappointing, but whatever, they work. And it wasn't like as an alternative I was going to go out and buy a set of $400 new telescoping gauges, so these will be fine. So you wouldn't typically use these in the automotive world, so I thought I would just very quickly show how they work, in case some of you haven't seen them before. These are for measuring internal diameters. And obviously this itself doesn't do any measuring, it's simply a way of transferring this distance. Hang on, I'm trying to find a place where you can see it and I can still operate it. How's that? So basically once the gauge is inside the circle, the force of the spring kind of centers it and finds the largest distance. And the idea is that you snug it up just enough to hold it. And then if you twist it, of course that distance is getting larger so it becomes loose without compressing the gauge anymore. And that should be the diameter of our hole. And so from there, where's the line? We can read the diameter. So this is 1 inch 250 thousandths. So that's how these work. Yes, it's a crappy old bandsaw. Nothing too exciting, I know. A little bit exciting for me because it means I won't have to cut everything with a damned hacksaw anymore. So I'm pretty excited to get this going. In fact, I don't need to get it going because it works. This came up for sale locally, and I live in a small town, so when something comes up like this, which I was looking out for, I jumped on it. Otherwise I'd have to wait for one to come up in one of the largest cities, and Auckland is about 4 hours each way for me, so to find one in my small town, yeah, I was definitely going to snap it up. Like I said, this works. It's a mid-90s Taiwanese model. I'm not intending to do anything to this, except we're just right now going to clean it up a little bit. This was in a workshop that was shared with a whole lot of woodworking gear and firewood and things like that. Well, I think it looks pretty good all cleaned up. I mean, nothing perfect, it's still the same scratched and rusty bandsaw it was before. But it's just a wee bit nicer to handle. I did end up giving the base another spray of paint. Just because, while it was dirty I couldn't tell, but when I cleaned the grime off, you could see really bad patches where somebody had painted it with some sort of, well, it kind of looked like almost a bituminous paint. So I just quickly scraped that off and sprayed one layer of black spray can paint over the top. Oh, and I put casters on the bottom. This is the ferry overdrive unit and the assorted levers and things that go with it. You can see these mounting holes here. This is where it attaches to the back of the gearbox. So this literally just slots into a hole pre-existing in the back of the gearbox. Anyway, let's clean this thing up and get it ready for storage. So this is the first time I've had anything to do with one of these overdrives. I don't know anything about it really. I don't know how it comes apart, and I haven't looked for any resources on how to get it apart. So we're figuring this out together. I mean, it's small, so it can't be that complicated, right? The first thing I notice is that these bolts are really, really tight. Come on, people. I had to break out the big 2-foot half-inch breaker bar to get them undone. And of course, breaking off the cap is accompanied by that sweet smell of stale old transmission oil. No, for real. Transmission oil stinks. The next day I was inspired to install door seals. But anyway, the selector shaft came out pretty easy. And now removing the main shaft. The obvious place to start is probably these circlips. I really have no idea how this comes apart, but we'll start at this end anyway. Well, at least the centre portion of the shaft seems to be moving pretty freely now. I don't think this large circlip is relevant at this point, and it's tough, so I moved on.
I'm pretty sure it's free, but just caught on something. I'll try pulling the lay shaft out before going any further. And the lay shaft just pulls out. I'm not actually sure what was holding it in the first place. I don't think there was anything holding it in. There might be something missing. Anyway, pulling the shaft out made it so that the lay shaft gears could just sort of randomly get more in the way. But with a little bit more shuffling, I managed to get the main shaft free.
You can see in here this small indentation. This unit here is the synchro mesh unit. It's the same as the first and second gear synchro mesh in the gearbox. And you'll see there's 3 of those little pockets. So floating around inside the case here, there'll be 3 little balls and 3 little springs. And then there's an outside ring that slots over the top of all of that. The ring was pushed off when I pulled this out, so hence the balls and springs have gone and found their freedom.
I pulled everything large and loose out, and then picking up the case and shaking it, there was a surprising lack of balls and springs falling out. Off camera, I did battle away and get that large circlip off, but it turns out I didn't really need to for now, because the bearing is actually pretty loose in the case, and I decided it would be easier just to remove the whole gear cluster. And now that there is nothing left in the way, the large lay shaft gear can just be pulled out. I was hoping the oil seal would just sort of flop out, because there's also a large needle bearing in the case underneath it. But it was going to fight me, so I decided to just leave it alone for now.
So here it is, all pulled down as far as I'm going to go. I have no reason to pull this oil seal or bearing out now. I really just wanted to get this cleaned up and have a general overview of the condition. A couple of observations. There should be 3 of these. There are only 2. There should be 3 little balls. There is only 1. There should be 3 of these springs. There are only 2, and one of them is mangled. Of course, those are the small spring and ball system that sits into these pockets. So there should be 3 of each. That tells me that not only have these fallen out, but they've come out with an oil change in the past and somebody has ignored the fact. And this ring is the outside that goes over these balls. You can see there is a ring through the center on the inside. That's the detent for those small balls. But you can also see in here that the gears are really buggered, to the extent that you might think it was supposed to be that way. But you can see where my thumb is, there's heavy indentation. And it's the same on the opposite side as well. Other than that, it's just a grimy mess. This oil is filthy and full of grit. So I will most likely be replacing all of the bearings. The actual large gears all look fine. I mean, no doubt there's some wear on these, but these are pretty hefty machined parts. Okay, so I'm just going to take this all outside now and give it a thorough clean. Well, that feels good. Everything's nice and clean, ready to go into storage. I hate storing things that are just a filthy mess to deal with later. Now when I come to actually rebuild this, I won't have to deal with a horrific mess to start with, which will be much more enjoyable. In terms of condition, this thing had really cruddy oil in it, so I'll probably end up replacing all of the bearings, and there are quite a few. None of them feel horrific though, so if for some reason I couldn't get a bearing, I'm probably okay. I would expect to replace the bearings in any rebuild anyway, so that's no big deal. This synchro unit, I will probably have to replace this. Well, I'll certainly have to replace some of it. I think I have balls and springs to replace these detents, but these teeth, especially in the outer ring, are so damaged, I'll probably end up replacing this whole unit. In terms of cost, I paid $600 for this overdrive. Now, given the condition and the amount of money I'll have to spend on it, that's not necessarily the bargain of the century. But these things go for big money. I would say though that you can buy a brand new Rover Drive, which is a considerably more modern design than this, for about $2,500 New Zealand dollars. So that's the window you're working in. If you're spending $2,000, you're wasting money. I should come in considerably under that. And of course my situation is slightly different in that rebuilding this will be a video and I'll recoup some of the cost. So anyway, I'm about to box this up and we'll see it towards the end of the Land Rover project. So this was a fairly big purchase for me, nothing too outrageous, but I decided to buy a set of ER25 collets and a chuck for the lathe. These are generic Taiwanese made collets. Purchased them from Arc Euro in the UK. Of course I can get ER25 collets in New Zealand, but the only ones I could get in New Zealand were similar unbranded collets of unknown origin, and they weren't cheap.
But mainly I bought them from the UK because I couldn't get the chuck or the square and hex blocks here, so it made sense to package it all together.
Yeah, so I decided to pull the trigger. A collet system is something I knew I would get eventually for the lathe, but it is a considerable investment. About 400 New Zealand dollars I paid for all of this. So yeah, I was reluctant, but it's done now, and I'll tell you why. You've probably all seen me use the lathe as a milling machine with a vertical table here, and an end mill just thrown in the 3-jaw chuck. Now there's two reasons why this sucks. The jaws on the chuck are hardened, as is the end mill, and trying to hold a hardened piece of steel with hardened steel doesn't really work that well. And every time this spins, it's really bad for the jaws. The second reason is that a 3-jaw chuck isn't perfect. It doesn't run perfectly true. So really when you're using an end mill in a chuck like this, you're probably only cutting on one flute at a time. Given how unstable using a lathe as a mill is in the first place, that really doesn't help. And I've got a few projects in the pipeline that I know are going to rely heavily on having to use this as a milling machine. So that's why I decided to bite the bullet and buy the collets now.
So this is the chuck itself, and as you can see, looking at the back of it, there's no way that this directly attaches to the lathe. You can buy chucks from Myford that are designed to screw right on, but this isn't one of them. This is an old back plate off another chuck, and this does screw directly onto the lathe. And all we have to do is turn the register on the back plate to match the register on the chuck. I noticed the thread on this backplate was a little stiff. I'm not sure why, but some of these old original backplates are just like that. And I bought a tap for this purpose quite a long time ago. I'd never try and hand cut a thread this size, but it's quite good just for chasing out existing threads. And this particular tap is pretty cheap because you can buy it from Myford suppliers in the UK. Any other size tap this large would cost a fortune. Okay, so it's time to start turning this backplate down. It's not like we have to make a backplate because that's already done for us. So this is pretty easy. All I have to do is turn the outside away, so we're left with a raised portion in the centre that perfectly fits the register on the back of the chuck. As I mentioned before, you can actually buy ready-made chucks to just screw onto the Myford lathe. Collet chucks, I mean. You can obviously buy ready-made 4 jaws and 3 jaws and things. But the whole point of a collet chuck is that it's really accurate in terms of being concentric with the lathe. The most accurate way to make a collet chuck would be to turn the chuck itself on the lathe you intend to use it on. That way everything's guaranteed to be concentric with the lathe. But I didn't want to do that, mostly because I can't be bothered, but also because my compound slide isn't very accurate and I would have had to use that to turn the taper for the collets themselves. So I decided, well, I'll just buy a chuck and turn my own register. I have a backplate here, I can easily turn that and everything should be sweet. And being the chump I am, I actually overshot with my cutting and had to recut it again. But now it fits perfect. The next thing to do is just transfer the position of the holes through to the backplate. This doesn't have to be particularly accurate. We're not relying on the screws for any sort of positioning. It's purely a clamping force. So I start by just going through with a 5mm drill bit, and then afterwards open the holes out with a 6.5mm drill bit to take M6 screws. The chuck came pre-threaded for M6.
Before I go any further, I want to see how true this is running. So I've got an indicator set up on the taper itself, inside the collet chuck. And you can see I've probably got about 1/1000th of an inch run out, which really isn't that great. But interestingly enough, it's not high on one side and low on the other. It's reading an oval shape. Now I doubt the taper is turned oval, so probably what's happening is our indicator is riding up and down the taper. So now I've got the indicator sitting on this turned section behind the thread. There's no taper to worry about here, so let's see how true it is. And I'm not sure if you can see that very well, but the needle is basically not moving at all. Yeah, barely moving, if at all. So that tells me that the register we cut is true. There's no problem there, and that the collet chuck is turning on the axis of the lathe, assuming they turned this part fairly well, but you would imagine they turned this and the taper in the same setup, so we don't have a problem with being out of line with the lathe, in other words. So what is going on? Now reading off the face of the chuck, and you can see we're about at least 2/1000ths, maybe 3/1000ths out of flat. And so that would explain why we were getting a misreading on the taper, because it was literally moving in and out, up and down the taper. So for whatever reason, the face of the chuck, well, not the face, the chuck is out of plane. I'm not sure if that's my fault or if it's the fault of the chuck. Let's do some further investigating. Okay, so now I've got the indicator just on the back plate we cut. Let's see how true that is. Looks pretty good to me. This is a rough surface, so there is some drag on the needle. But you can see if I'm consistent, the needle is really only picking up the roughness of the surface. Definitely not that 3/1000th waviness that we were seeing on the outside of the chuck. The obvious and most likely cause is that there was something between the two pieces, or that it wasn't tightened down evenly. But while it's apart, let's check this. So I'm not exactly sure how this was made in the factory. I mean, they may have had clever machines which can handle the whole operation in one. Obviously it would have been done on a CNC machine. But it's possible that the features on this side were turned separately to the features on this side. So let's check the thickness here and see if there's any obvious problems. Oh yeah, this reading is very different. This is metric because that's easier for my brain, but since we've been talking thousandths of an inch on the indicator, I'll quickly go and get a imperial micrometer. Okay, so we're basically at 12 thousandths there. And here we're more like between 14 and 15, just over 14. And right here we're down at 12. 12. Just under 12. Just over 14. Over 14. 14. And then dropping back down. Okay. So in other words, this chuck is 2 thousandths out of flat between the two faces. That's not something I can just make go away. I mean, I could of course just hold this in the lathe and take a skim cut, but that's really difficult for me with what I have to get all of that lined up. I mean, I guess we'll have to try, but yeah, that's not going to be straightforward. Okay, so I'm putting the part in the 4-jaw chuck. The only reason I'm using the 4-jaw is because it's got a large enough centre here for the thread to clear. I'm not worried at all about alignment this way. I will check that we're roughly concentric and see what the readings on our face look like. You can see the two marks. I've got a mark here. Can you see that? Yep. I've got a mark here and here. This measured something or other in 12 thousandths. This measured something or other in 14. So in other words, we're 2 thousandths higher than here than on this side. Now if we get lucky, just simply putting it in the jaws will compensate for that. Otherwise I'll have to shim it or bump it around or whatever to try and get a reading that matches these numbers. And then we'll take a skim cut to remove that difference.
And yeah, here you can see the indicator readings off the face. So just pushing the piece up against the jaws in the 4-jaw was pretty close. This 4-jaw chuck is a fairly high quality product, so we got a nice flat surface by just pressing against the jaws themselves. And now the indicator reading is roughly matching what we measured with the micrometer and where I've put the markings. It's really difficult to get this perfect. We're talking about a part that's about 100 millimeters wide, and trying to align the face of it within 1/1000th of an inch over that distance. Yeah, this is definitely not the way you would do this if you were making a part from scratch. Don't worry about the part wobbling in the picture here. That's because it's not centered in the 4-jaw. Basically because I'm lazy, and it doesn't really matter for the sake of taking a facing cut. And it turns out this chuck must be a little hard. That's the squealing you can hear. It's a little too hard for high-speed steel. I did persevere through one cut because I don't really have any carbide. But you'll see in the minute I managed to dig something out. Ah, that's a bit better. This is actually a carbide threading insert. So not really designed for taking facing cuts, but it's a hell of a lot better than pushing through it with high-speed steel. So to cut a long story short, I ended up repeating that process about 3 times, I think, measuring in between. Like I said, it's difficult to set it up perfect, but despite that, I did get the chuck pretty flat. By that I mean the back surface parallel with the front. But as you can see, that didn't really help anything. In fact, it seems to have made things worse. Measuring on a piece of round bar held directly in the collet, you can see it's pretty horrific. That's about 5 thousandths, which is totally unusable. So at this point I came to the conclusion that I wasn't going to be able to fix this using the method I was. There obviously isn't the relationship I thought there would be between the taper being cut and the other features machined into the front of the chuck. And by this stage, I was pretty much resigned to the fact that this chuck was going in the bin anyway. I did send an email to the company that sold it to me, and then I decided to stop wasting my life on this chuck today, and went and did something else for a while. And the following morning, being a little less frustrated, but still pissed off that they sold it to me like this, I decided to mount the chuck in a different manner that would allow me to machine it more directly, although it is a little bit more of a precarious setup.
Basically, I'm going to hold this in its own collet and turn this back face. In theory, that should cut a pretty accurate surface, but there's a lot of wobble and precariousness involved in that setup. At this point, we've got nothing to lose, so let's give it a try.
Okay, so I'm turning a piece of round bar in the lathe, partly because it's too large to fit inside the largest size collet, but also because I want to turn it on the lathe so that the piece of bar will be perfectly concentric with the lathe itself. And I was careful to let the part cool down before taking a final skim cut. I really don't want this part shrinking or losing accuracy after I put the collet on it. Instead of holding a part in a chuck, we're going to hold a chuck on a part. And once again, using the long suffering threading insert, just take a simple face cut. And you can hear the part chirping at the start of the cut. That means it's definitely not flat, which is a good sign because there should be something wrong for us to fix. And that's it. Let's see how it turned out. Honestly, I can't say I was expecting that.